This video covers the Unit 8 review dealing with solution, solubility, concentration, dilution problems, and acid-base titrations. As far as physical properties of water go, they are basically properties that you can observe without changing the identity of the water. Some of them include the water is colorless, boiling point of 100 degrees Celsius or freezing point of 0 degrees Celsius. That doesn't change the identity of the water. It's a change in state, but when you boil it, it's steam, it's still water. Same thing when you freeze it. It's no longer liquid, it's in the solid phase, but it's still water. High surface tension, this you've demonstrated by dropping droplets of water like on a penny and how they form a bubble, or how you can fill a glass greater than its volume and you have that big surface tension bubble on top. That's largely due to the fact that water molecules stick together due to hydrogen bonding. Water molecules are polar, which means they have regions of positive or negative charge. You've demonstrated that they have electrical charges. You may have introduced a static charge, either off a balloon or off maybe a rod that you stroked with some cat fur or rabbit fur, and it attracted a stream of water to it. And then finally, density. Water has a density of 1 gram per milliliter. To explain hydrogen bonding, you will note anytime you have a water molecule, you have hydrogen atoms and oxygen atoms sharing electrons. Just because they share, it does not mean that they share equally. Oxygen is far more electronegative than hydrogen. It has a value of roughly 3.5 compared to hydrogen's 2.1. So the electrons spend more time around the oxygen than they do either of the hydrogens. What happens is you end up having a net negative charge on this end and a positive charge on this end. And so you have what is known as a dipole. So two opposite ends, a negative and a positive. You will notice this symbol, that is the lowercase delta. That means slight or partial. Because the electrons spend more time around oxygen, it becomes negative. If you are a hydrogen atom and all you have is a proton and an electron, and your electron is gone, you're positive. You will notice that adjacent water molecules, there is some attraction between the hydrogen of one water molecule and the oxygen of the other one. That is the hydrogen bond. It is an intermolecular force between two molecules. And here is just a diagram showing hydrogen bonding between 3 adjacent water molecules. And so it's very similar to the last one. You will note that you have attraction between the hydrogens of one water molecule and oxygens of another one. So that would be how you would demonstrate hydrogen bonding between 3. Ice is less dense than water. How do you know? Because ice floats on water. As you recall, density is just mass per unit of volume. If you look at these two diagrams, you'll notice that these squares are roughly the same size. If you were to count the number of water molecules in this square compared to the number of water molecules in this square, you'll find there's a whole heck of a lot more of them here, and you can see they're really packed in there tightly. Here, you notice there's air spaces in between. Okay, this first diagram, the one on the left, is showing liquid water. Okay, and this diagram is showing ice. You will notice that when water freezes, it forms these regular geometric patterns, and there's air spaces in between there. Because of that, this is one of the factors that causes ice to expand as it freezes. This is what causes frost wedging and all this stuff, causes potholes in the spring. It'll burst your pipes in the winter if you don't heat your home. Also, if you put like a pop in the freezer, the expanding water will rupture the can of soda. So anyway, water, there's more per unit of area. It's denser than ice. Okay, when explaining the difference between polar and nonpolar molecules, basically there's two things that influence the polarity of a molecule. The first thing is the electronegativity between the two elements that are bonded. So basically their attraction for a shared pair of electrons. The other thing deals with geometric shape. We haven't gotten into a lot of geometric shape stuff yet, but generally just know polar, the electrons are shared unequally, which means like in a water molecule, the oxygen has a stronger attraction, therefore it becomes slightly negative. The remaining hydrogens are slightly positive. If you have something that is nonpolar, they are generally shared equally. One other thing, though, I did want to mention, if you look at some of these shapes, And we're not going to get too far into this, but I just want to mention to you, you will notice, okay, really all of these molecules contain polar bonds, because if you look at any of these diagrams, you have these little arrows with like a hash mark or a line that's demonstrating that these are definitely polar bonds. The electrons are coming from the atom that has the plus end on it and going towards the one that has the arrow pointing to it. So notice some of these, like here you have hydrogen chloride or hydrochloric acid. This is definitely polar because the chlorine has a stronger attraction for the electrons than the hydrogen. Same thing here with ammonia. The nitrogen has a stronger attraction and all the electrons move toward it. This molecule has a specific shape. This one is called a trigonal pyramid. This is not equal and opposite. It is not symmetrical, therefore they don't cancel. You'll notice here you have boron trifluoride. This one is called trigonal planar. This is symmetrical. These are equal and opposite. They cancel, making it nonpolar. Same thing here. This is a special shape called a tetrahedron. You will notice a tetrahedron is symmetrical. It looks like a pyramid base with a hat, but no matter how you flip it, it looks the same. It is symmetrical. It is nonpolar. This is another tetrahedron, but you notice this is not all equal and opposite. It only has one polar section. Just the carbon and chlorine bond is polar. The carbon and hydrogen share equally, so this molecule, even though it is in a symmetrical shape, they're not all equal and opposite. This would be a polar molecule. So the same thing over here. I guess this is just a repeat of this diagram. And believe it or not, this is a repeat of this one. I don't know why I put it both on there, but there you have it. All right, for examples of solutions, colloids, and suspensions, and how the Tyndall effect can help you distinguish between them. Basically, a solution is homogeneous, which basically means it looks the same throughout. Aqueous solution is one where water is going to be the solvent, and then the solute is the thing that is being dissolved. So an example like salt water is a solution. When you shine a laser beam through a solution, no light is seen. Okay, why? The particles are interspersed and they're so tiny they don't reflect even light. So there's no beam of light present in a solution. A colloid is a heterogeneous mixture containing particles large enough to scatter light. All right, so you're looking at things like, for an example, milk or fog are examples of colloids. In milk, you have like little fat globs that are floating around in water. That's what milk is. Or fog, you have suspended water droplets in gas, the atmosphere, which is just really, it's a low-lying cloud. The thing about colloids is that the particles are not large enough to settle out. They stay kind of just suspended in that colloid, and gravity does not pull them to the bottom. You don't have to shake milk up before you drink it. It's just ready to go, ready to pour. A suspension, the last one, is also a heterogeneous mixture, but it has particles that do settle out when you let them stand. So, for example, if you go down to the river and take a glass of water and pull it out, you'll definitely see all the suspended load, all the sand, soil, clay, all that stuff that's suspended in the water. If you let it sit undisturbed and the water isn't churning, that stuff generally will fall to the bottom. And so colloids and suspensions, they generally will demonstrate the Tyndall effect, meaning you will see a beam when light passes through them. Suspensions, you know, it depends. If they've sat undisturbed long enough, then they may not show the Tyndall effect as strongly, but generally they do. Okay, to describe what happens to the solute and the solvent when an ionic compound dissolves, if you will look at this diagram, okay, you will notice that all of these are little water molecules. So these little red dots are the oxygens, and then the little white dots hanging off of them are the hydrogens. As you realize, water is a polar molecule, and so what happens is as they encounter ionic substances like here, this is a crystalline salt, this is sodium chloride, you will notice that the positive hydrogen atoms orientate themselves in a way in which they surround the negative chloride ions. And so they kind of trap them here in their own little magnetic bottle. All these positives are surrounding this central negative. Likewise, you'll see that the sodiums are positively charged And notice the water molecules, all the negative oxygen ends of the water molecules surround the positive sodium. So it keeps it away from the chlorine in its own little separate magnetic bottle. And so this is how water will dissolve ionic substances. Okay, when defining these terms, unsaturated is basically just a solution that has less solute than it can hold at a given temp. Basically, that means it has the ability to dissolve more stuff. It's got more room. A saturated solution is generally going to be a solution that holds the maximum amount of solute that it can at a given temperature. Generally, when you see something that is saturated, if you put more solute in it, the solute will just sit in the bottom in its solid form generally. Supersaturated, you guys witness this in the laboratory. When you supersaturate a solution, you'll have a solution that is saturated, one that cannot dissolve any more stuff. You basically then will heat it up, which will allow the solution to dissolve more of the solute. When you allow it to cool back down, as long as you don't disturb it and let it cool, kind of slowly, just there on its own without disturbing it. The second you disturb it, or you like add another seed crystal, that extra solute will precipitate out, and it does it very quickly. Okay, a couple of things you need to be aware of solubility. So generally for salt, that means it's generally going to be an ionic solid. As temperature increases, the solubility of a salt also increases. So they are directly related. As one gets bigger, the other gets bigger. As one gets smaller, the other gets smaller. Gases are the exact opposite. So as the temperature of the gas increases, the solubility of the gas decreases. And you witness this in your amount of carbon dioxide in pop lab. As the soda warmed up, the more CO2 came out of it. Why? It couldn't dissolve as much. I've also given you the example of like fish kills. So sometimes bodies of water, lakes and so forth in the summertime, as the temperatures get really warm, they can't hold as much dissolved oxygen. Well, fish need oxygen to breathe in order to live. So if there isn't a lot of oxygen in the water, fish start dying off in huge quantities. Okay, so basically the next 5 problems deal with reading a solubility graph. Your numbers may fluctuate if you have another table you use from your textbook. This one is asking for the mass in grams of sodium chloride that will dissolve in 100 grams of water at 9 degrees Celsius. No matter where you get the information, the numbers will be somewhat close. They might not be exact, but this is just an exercise in reading graphs. And so if you look at this, so here's 90 degrees Celsius, and sodium chloride is this line here. And so if I follow this graph up, 90 degrees Celsius, sodium chloride, it's a little bit below 40. We'll just call this 38 grams of sodium chloride. Okay, in this problem, you're dissolving 20 grams of potassium chloride in 100 grams of water at 40 degrees Celsius. And so therefore it says the solution will be unsaturated. So let's take a look here. So it says 40 degrees Celsius and 100 grams of water, and it's saying potassium chloride. And so potassium chloride is this line right here. If you follow it up, it looks like it can hold roughly 40 grams of the solute. Okay, so if it can hold a maximum of 40 grams, but it's only holding 20 grams, you can dissolve 20 more grams of the salt in that solution. Okay, and looking at this problem, it wants to know the minimum mass in grams of 70 degrees Celsius of water that is needed to dissolve 80 grams of potassium nitrate. And so if you look at 70 degrees, okay, 100 grams of water will dissolve, and potassium nitrate's clear up here. It's right at about 140 grams is how much it will solve. So what we need to do to solve this is we need a proportion. Well, I know that 140 grams of this salt will dissolve in 100 grams of water. And I want to know what is the minimum amount to dissolve 80 grams of the salt, so 80 grams of potassium nitrate, and I don't know the mass of water. How do I how do I solve for this? I have to cross multiply and divide. So essentially this fraction turns into x equals 80 grams times 100 grams divided by 140 grams. And so if I enter this into my calculator, 100 times 80 divided by 140, you're going to get, the answer should be 57 grams. Well, I didn't notice before, but this graph doesn't have oxygen on it, but no sweat, I can just give you the values. Basically, if you look up on a chart, you're going to find the solubility of oxygen gas, well, 0.0043 grams of oxygen will dissolve in 100 grams of water. And it wants to know the mass of oxygen, so that's going to be your unknown. That'll be dissolved in 1,000 grams or a kilogram of water. Well, basically all you end up doing is, to solve for this, you're going to cross multiply. So it's going to be 0.0043 times 1,000 divided by 100. When you do that and solve, you get 0.043 grams of oxygen. Okay, with this question, it's asking for the mass of potassium chloride that will produce a saturated solution in 500 grams of water at 20 degrees Celsius. And notice it even tells you the solubility of potassium chloride is 34. And if you look, sure enough, here's 20. You go up, and here's potassium chloride. It's right around 34. And so all you have to do then, make a proportion. Okay, so I have 34 grams of the salt in 100 grams of the water. And I want to know how many grams of the salt could be dissolved in 500 grams of water. So essentially you cross multiply, so 34 times 500 divided by 100, the answer should be 170 grams potassium chloride. Okay, I apologize, this graph does not list the silver nitrate on here either. I didn't, pay attention to this, but first off, okay, it tells you, if you look at a graph, it says 20 degrees Celsius, 100 grams of water will dissolve 222 grams of silver nitrate. And then if you look at the graph and you read, okay, 50 degrees Celsius, it'll dissolve 455 grams of silver nitrate. So it wants to know how much more can be added to make a saturated solution. Well, 455 grams minus 222, 233 grams of silver nitrate could be added to this saturated solution, and heated up to 50 degrees, it'll dissolve that many more. Okay, to calculate molarity, just remember this is the formula. Molarity is equal to the moles of solute per total liter of solution. So all you have to do is substitute in what you know and solve for what you don't. So if I want to know the molarity of this, and I know that this is I have 0.40 moles of NaCl, and I know that I have 1.6 liters of solution. If I put 0.40 in my calculator and divide by 1.6, I get 0.25 molar. That's the answer for the first one. Okay, for the second one, I have 20.2 grams of potassium nitrate, and I have 250 milliliters of solution. I'm going to have to do calculations for both of these. The first thing I have to do is I have to find out how many moles 20.2 grams is. So I start with what I know, 20.2 grams of potassium nitrate. Well, I look up the molar mass, and I know that 1 mole of potassium nitrate, well, if I add up their masses, I find that its molar mass is 101.11 grams of potassium nitrate. Grams of potassium nitrate cancel. I take the 20.2 divided by 101.11, and that's going to tell me that I have 0.19978 moles, and so I'm going to round that to 3 sig figs. It's going to be 0.200 moles of KNO3. And then I take the moles of solute, I divide it by the total liter of solution. Notice that these units are in milliliters, so I must convert that to liters. How do I do it? It's going to be basically 250 divided by 1,000. You're essentially moving the decimal place 3 places to the left. And so what this becomes is 0.2500 liters. If I put this in my calculator, you're going to find out this is 0.8, and then for sig figs you need 3, so 0, and the unit is molar. Okay, in this situation I know the molarity, so I have 0.85 molar. I do not know the number of moles, but I do know the volume, 0.0250 liters. You must convert it to liters. If you multiply both sides by 0.0250 liters, okay, this goes away, and you solve this, you're going to have a number with 2 sig figs, 0.021 moles of potassium bromide. But notice it did not ask for moles, it's asking for grams. So how do you find grams? Well, I know that 1 mole of potassium bromide, you want moles on the bottom so they cancel, and it has a mass of, if you add them up, it's 119 grams of potassium bromide. So 0.021 times 119, the answer, 2.5 grams potassium bromide. Okay, this is a dilution problem. As you guys recall, here's the formula for dilution. The molarity of the initial substance times the volume of the initial is going to be equal to the final molarity times the final volume. The nice part about these problems, the volume you do not have to convert to liters. You can leave them as milliliters and the units will take care of themselves, cancel or be remaining if that's what you need. And so if you look at this, a couple ways you can do it. All right, so let's say I want to put 0.500 molar for the initial molarity, and I don't know what the volume is, but I know that the final molarity is 0.100 molar, and the final volume is 100 milliliters. Okay, how do I solve for x? If I divide both sides by 0.500 molar, the half molar cancels on both sides. The molar cancels over here, so you have 0.1 times 100 divided by 0.5, and if you do that, you end up with 20 milliliters is the final volume. Okay, now notice how this problem is worded a little differently than the last one. This is asking how I would prepare the solution, and so let's see. I'm going to go with the initial molarity 1.25 molar. And the volume I do not know, but the half molar I know goes with the 200 milliliters. And so I'm going to solve for x and divide both sides by 1.25 molar divided by 1.25 molar. The 1.25 molar cancels, the molarity cancel, and so if I punch this into my calculator, x, so I have 0.5 times 200 divided by 1.25. And if I do that, I get 80 milliliters is my answer. But notice it's asking how would I prepare this. So this would be 80 milliliters of the solution, and then what I would add to that. So to make the total of the 200 milliliters, and I have 80 mils of this solution, what do I have to do is I have to add 120 milliliters of water to dilute that up, and then the total is going to be your 200 mils of solution. So, I mean, the way this is worded, so how would you prepare? You would need both those quantities. So the 80 mils you solve mathematically, and then how much water you would take to dilute up to that final 200 mils.